Hi, this is Sri Ranjani. In this video, we are going to see the reference signal generation using modified synchronous reference frame. Here already you have seen that when the load is linear load, non-linear load as well as a linear load, when you use the highly inductive load, then the supply current lags the supply voltage. So power factor is low. So in this case, while you are finding the reference signal generation using conventional SRF technique, then the current lags the reference current will be generated, that is fundamental component current will be generated using the SRF theory, but the current is reference signal is not in phase with the supply voltage. So the current lags the supply voltage. So we have to modify the SRF algorithm for the reactive load. So here we are taking the three-phase supply, and then inductive load is same inductive load what we are taking 8 ohm and then 20 millihenry, and DC load is 20 ohm, and supply voltage all are same 230 volt 50 hertz. RMS peak voltage, so 230 into root 2. In the same way, Y phase is minus 120 degree phase shift, and B phase is minus 240 degree. Then the RMS value is calculated for the voltage VABC and IABC. This is the voltage and the current measurement block. We are using the label as VABC and current as IABC. Then we are finding the power, voltage and current using the single phase power unit only we are using. So we are using the Dmax, and we are taking R phase voltage and current, and it is connected to the Dmax to get the power and reactive power, active power and reactive power. Then the Fourier block is connected in order to get the RMS value. Magnitude we will find out. Then the magnitude is connected to the gain block. So Vm by root 2, 1 by root 2, that gives the RMS value. So in this reference signal generation, we have the unit of ABC to DQ transformation. So if you see that here IABC and VABC, it is taken from the measurement block. So from the measurement block we are getting that IABC and VABC, that is given to the ABC to alpha beta gamma equation. So the gain block we are taking, so this is the equation we are constructing first. So this is the gain block where the 2 by 3 into first row semicolon, then second row semicolon, third row, then close the bracket. Here you take the multiplication as matrix K star U. So then we have to convert that alpha beta to DQ component. So we need the cos omega t and the sin omega t term. So the omega t we are getting from the PLL. So this is the voltage input. The voltage is connected here. So this is a VABC. So here the only changes we have to do it is frequency. If you are doing by 60 hertz, then you can use 60, or if you use 50 hertz frequency, use the 50 hertz frequency. Remaining all are the default value, you have to take it. So from this omega t, you can use the trigonometric function, sine term, and then use the cos term. So you will get that cos omega t and sin omega t. So from this ABC to alpha beta gamma, you will get the 3 output. So u of 1 to u of 3, you will get it. Here sin omega t is u of 4 function to this mux, and cos omega t is u of 5. So then this mux output is connected to the function block here. So in this function block, you will get the DQ component. So cos theta into alpha, I alpha plus sin theta into I beta, you will get the D component here. and then Q component you are getting this term. Then we are finding the mean value. Here what we are doing here is we are getting that D average and Q average. So from using this D average and Q average, we will get the magnitude of this term. So we will get that Q term alone, D we are taking as 0. Why? Because here this is the modified algorithm. So we are finding the magnitude alone and we are keeping that D as 0. So D as 0, only Q component we are getting. Then that is connected to this, again the transformation of dq to alpha beta and then alpha beta to VABC. So when we are doing like this, so dq component and then same ABC, PLL circuit, then trigonometric function, sine and cos functions, then that is given to the function block of this. Here we are getting dq only, so u of 1, u of 2 in the first mux line and sine function in the this mux line and then cos function. So u of 1, u of 2 and u of 3 is the sine function and u of 4 is the cos function. So using this one we can form the equation here. So we are getting the conversion alpha to beta. From alpha to beta we can convert into the ABC component, that is the reference signal. So that component we are getting here. So here it is represented in terms of V. Actually it is a I component, not the V component, I component only. So from this I alpha, I beta, I naught, we can get that IA, IB, IC. So the notation is represented V, but it is the current value only. So this gain block, that first row we have to enter it here, then semicolon, second row, semicolon, then third row, semicolon, third row you have to close the bracket, and multiplication you have to select this matrix K star U, you have to select. Then that will give you the sine wave, that is fundamental current sine wave it will give. Suppose you want the harmonic current as the reference signal you are taking, then you can subtract that actual current with this fundamental so that we will get the harmonic current. So now we will run the simulation and we will see how it is working. So now you can see that while it is running, it will show the magnitude value and also RMS value. We will check it whether we are getting the same RMS value. So now for 0.1 second stop time, we will run the simulation. We will check it, what is the RMS value we are getting. So here we are getting the 41 as the fundamental current RMS value. The same RMS value we are getting here also. In previously, without modifying that reference frame, only the synchronous reference frame we have taken. Here if you see that the fundamental current is 41, but here fundamental current is 50.62. Then the reference signal, if you see that there is a lag in the reference signal, but if you see the reference signal of this modified SRF, the signal will be in phase with the supply voltage. So this is the reference signal, then this is the harmonic component. So for inductive load we can prefer the modified SRF. Even inductive load or any other component we can use this modified SRF. We will get the accurate result for any compensator, shunt active filter or any compensator, inverter circuit, it will be working